Okay, so here with example 3, keep going on with what we've been doing. First of all, we want to do is just look at our domain. X to the cube root of x squared looks great, times x minus 5 looks great. It's just kind of like a polynomial. All right, the first thing, so the domain's all good, and let's find our x and y intercepts. So our y-intercept will be when x is 0. So obviously, when I plug in x to be 0, 0 to the 2/3 times anything is going to be 0. Now to find my x-intercept, we're going to go y is equal to x to the 2/3 times x minus 5. This first point, specifically I guess I should say, whenever we do our y-intercept, or x-intercept, put 0 right there. This first factor is going to give us a x-intercept of 0, and the second one of 5. Okay, so now when I want to go and take the first derivative, I think what I'm going to do is rewrite my function and actually distribute it so I can see, and so I don't have to do the product rule. So 2/3 plus 1 will be 5/3, and then minus 5x to the 2/3. Okay, so now we can find the first derivative. We'll get y prime to equal 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. Okay, and then from there, we set our first derivative equal to 0 in order to find our critical points. So 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. Okay, so moving the 10/3 over, we have 10/3 x to the negative 1/3 is equal to 5/3 x to the 2/3. And if I multiply both sides of the fraction, let's say, just to kind of clean this up with the coefficients in front, let's multiply both sides by 3/5. Okay? And that's going to give us 2x to the negative 1/3 is equal to x to the 2/3. So hopefully at this point you all can see right away that we're going to have a critical point x equals 0. Because first of all, plugging in 0 for the bases will give you 0 equals 0, so that's going to check out. What we could do to both sides to kind of further clean up, we could cube both sides so we can get rid of those fractional exponents. So that would be 8x to the negative 1 is equal to x squared. Okay, and then from there, if we write that as 8 over x is equal to x squared, multiply both sides by x, you'll get 8 is equal to x cubed, and then if we take the cube root of both sides, you'll get x equals 2. Now technically I could cube, I'm sorry, I was thinking I could cube positive 2, negative 2, but no, negative 2 would be negative 8, so it's just x equals 2. So there's another potential critical point, is at x equals 2. Okay, so if we go to y double prime, the second derivative, we're going to get 5/3 times 2/3, so 10/9 x to the negative 1/3 plus 10/9 x to the negative 4/3. Okay, from there, if we set it equal to 0, and if we want to, it's like, what would make it easier for us? We can go ahead and factor out the 10/9 if we want to. We can factor out technically 10/9 x to the negative 1/3 if we want to. And what that's going to leave behind, here, let me fix that exponent, that looks kind of weird. To the negative 1/3. And then that's what's going to leave behind is 1 plus x to the 4th. And I'm sorry, not 4. It should be just 1, right? It'd be, if I was raising each of the powers, then that would be work, but because if I would distribute it back in, it'd be 10/9 x to the negative 1/3, and then what do you have to add to negative 1/3 to get negative 4/3? So there should be a negative 1 right there. Wishful thinking on my part, but still not that bad, right? Okay, and then if we set each of these factors equal to 0, you're going to get a point of inflection at x equals 0, and then you'll get another one. If we go 1 plus x to the negative 1 equals 0, that's basically saying 1 plus 1 over x is equal to 0. So 1 over x is equal to negative 1. Okay, let me clean up some of this other work here that we don't really need anymore. Or, if you take the reciprocal of the left and then take the reciprocal of the right, it's telling you at x equals -1. Just flip this left side, and the reciprocal of -1 is -1, and there you go. Okay, so let me clean this up real quick and kind of write out some of our key points, and we'll be right back here in just a second. Okay, so I just erased basically the work where we said the derivative is equal to 0, and I just highlighted it here. So our critical points that came from our first derivative are at 0 and 2. And then the ones we're going to test for our points of inflection for our second derivative are going to be -1 and 0. Okay. So like before, like we always do, let's test them individually and see if we can come back with the same sign value. So once you pause the video, let's test together, and then we'll come right back. Okay, so coming together, hopefully y'all kind of got the same thing that I did. Let's go through here and just try to draw a graph. Okay. So basically we have x-intercepts and a y-intercept. So why I wrote that as x, I have no idea. But y equals 0, and then we have 1 at 5. Okay. Keep drawing our graph just a little bit more. So we know those 2 points. Some other points that we also know is that going from positive to negative, so going from increasing to decreasing, that at 0 I have a max. And going from decreasing to increasing, at x equals 2 I have a min. Okay, so there's a low point there. And actually when I plug that into my calculator, there at 2, I get a value of about -4. Okay, so that's a good point to know. Okay, another point that we also want to know is about our points of inflection. So we're going to be concave down all the way up to -1, and then we're going to be concave up the rest of the way. Okay, so at -1, let's find that point. When I plug -1 into my calculator, I get -1, -6. So we have a change in concavity right about there. Move this down a little bit. I know I'm kind of going over that other function, but yeah, I'll come back and erase. That's what erasers are for. Okay, so we're going to be concave down, kind of coming up to that point. We're going to be concave up to 0. And I know that 0 is a max, because that's what it tells us in our first derivative test, so I don't have to go through it. I stop right there. I know that at 2, down here at -4, that I have a min, and my graph tells me that from, let's see, 0 to beyond, I'm going to be always concave up the rest of the way. Okay. I'm decreasing from 0 to 2. That's what my first derivative tells me. And then I'm increasing past. And always concave up in here. Decreasing from 0 to 2 and increasing from 2 beyond. And so there's an idea of what our graph's going to look like for this function. Okay, so let me erase some stuff and let's go on to part D.